مرحبا. أنا إيناس وراح أحكي عن ال transmitters والfull AM modulator. Okay, so to start with, transmitters produce a signal with a specified type of modulation using the right carrier frequency and with enough power so that the output signal is coupled with an antenna. The modulation must be accurate so that the received signal at the receiver is as close as it could be to the original modulating signal. Okay, so there are six requirements that should be considered when designing a transmitter. The first one is the accuracy and the frequency accuracy and stability, which are fixed by the carrier oscillator and specified depending on the application of the transmitter. The accuracy of the output frequency is controlled by a crystal synthesizer. And the second requirement is the frequency agility, which is the ability of the transmitter to change the operating frequency to account for mutual interference from other sources. The third requirement is spectral purity. So all transmitters produce false signals that are harmonics of the operating frequency. These frequencies must be filtered out to avoid interference, leaving the assigned transmitting frequency to achieve spectral purity. The fourth requirement is the power output. So the power output of the transmitter is measured depending on the modulation used. For full carrier AM transmitters, it's done in terms of carrier power, where peak envelope power is used. And for FM transmitters, they are rated in terms of the total power output. The fifth requirement is the efficiency of the transmitter. So the transmitter efficiency is important for energy conversion when large power levels are involved. So in addition to the energy conversion, the power that enters the transmitter from the power supply and does not exit from the antenna should be considered when achieving high efficiency. Where it's converted into heat in the transmitter, and dissipating it requires heat sinks and fans, which add to the cost of the equipment. In calculating the energy cost, the overall efficiency is what should be considered, and it's the ratio of the output power to the input power. The overall efficiency is reduced by losses in the power supply and the tube heater power. So the last requirement is the modulation fidelity. So in order to have an ideal communication system, the original signal should be recovered exactly at the receiver. So the transmitter should modulate any base band frequency onto the carrier and any modulation level so that the baseband spectrum must be restricted to keep the transmitted bandwidth or the transmitted bandwidth within the appropriate limits. So in addition, compression is used to keep the modulation percentage high, where it distorts the original signal by reducing the dynamic range, which results in an improved signal-to-noise ratio at the receiver. Okay, so we have three main transmitter topologies. The first one is the high-level modulation. So this type of topology is used where modulation happens at the last stage before the antenna. Okay, so as we can see here, there are three main blocks that I'm going to talk about, which are the buffer, the driver, and the matching circuit. These three have almost the same function. So starting off with the buffer, It has a gain of 1 and it isolates the oscillator from the remaining circuit and matches between the oscillator and the next block. So to be clear, when matching or power matching is when the input impedance has to be equal to the output impedance of the previous block. So the Z output or the impedance output should be equal to the conjugate of the Z input. It's also to used to reduce the noise and the harmonics produced. So without matching, there will be losses and the maximum power transfer will not be achieved. Moving on to the driver. The driver contains nonlinear elements such as transistors and transfers all the power present in the previous block to the next block, and it might also add additional power. And for the last block, which is the matching circuit has two types that I will be talking about later. It matches between the antenna and the power amplifier. It also contains passive components or linear components and does not cause distortion or produce harmonics. Okay, the next topology is the low-level modulation. So low-level modulation happens in a stage that is further from the antenna, and it involves changing the transmitted frequency, such as in FM. So as you can see here, the frequency multiplier block is optional, where it multiplies the frequency deviation and the carrier frequency. So this type of modulation is used basically in FM. Because the last topology we have is the heterodyne system. This system is more complex or a more complex design than the previous two topologies discussed. It's used to modulate the signal at a fixed frequency, and it's basically used for a single sideband surplus carrier. So this type of system is mostly used in transmitters nowadays. Okay, moving on to the power amplifier and modulator. This circuit is used for AM, and the information is presented on the amplitude. Therefore, the power amplifier has to be highly linear because any distortion caused will affect the information to be transmitted. So this is a Class C modulated amplifier, and since Class C has the most distortion among the other devices of classes A, B, and AV, but it has the highest efficiency, therefore it will be used to design the AM modulator. Class C has only one transistor as shown here, which is biased in the cutoff region. And the power dissipation of this device is very low because the time in which the device is activated depends on delta T. And for small delta T, the power dissipation decreases. So in this circuit, we have two types of capacitors. The first one is the audio bypass capacitor, and the second is the RF bypass capacitor. So the audio bypass capacitor acts as a short circuit so that the audio signal does not change the DC value or the VCC, as we can see here, so that we get a pure DC signal. And the RF bypass capacitor also acts as a short circuit so that the RF signal coming from the source or the input does not overrun the voltage at node A, so that it does not get interrupted by the RF signal. Okay, so we want this modulator to produce this equation or this voltage as shown here, which is VTAM. And we know that class C output is VCC cosine omega nt. So at VCC, there should be a DC and an AC component, which are represented by N here. So E carrier is the DC component, and EM cosine omega mt is the AC component. So the supply voltage should have this form. So the voltage at the audio transfer or node A is equal to VCC plus EM cosine omega mt. Therefore, the output voltage is equal to this voltage multiplied by cosine omega c. So to recap, the voltage here at node A should be VCC plus EM cosine omega t. And the output produced should be cosine omega c multiplied by this output. So the amplitude or the output amplitude is the voltage present at node A, and therefore this produces AM modulation. Okay, so the circuit design, for the circuit design, we need to determine 3 parameters from the carrier power. The first one is the audio amplifier power, represented by PA. So starting with the audio amplifier, we know that the total power is equal to the carrier power multiplied by 1 plus m squared over 2. And assuming maximum power at m is equal to 1, this should be 1. The total power is equal to 1, is equal to the carrier power multiplied by 1.5, since this becomes 1. And we know that the efficiency for class C at m is equal to 0 is PC, or the carrier power, over the supply power. So at the maximum power, the efficiency is equal to 100%. Therefore, the carrier power is equal to the supply power. And since the supply power does not change and the carrier power changes due to the efficiency, the power, or the audio amplifier power, at the maximum voltage is equal to 0.5 PC, which is also equal to 0.5 PS. Now for the audio amplifier impedance, it will be calculated using the power at the transformer. So the power at the transformer is equal to VRMS squared over ZA. And assuming maximum power, all the power goes to the transformer side and not the amplifier. So and assuming a 1-to-1 ratio, the voltage is equal to EC plus EM cosine omega mt. So at m is equal to 1, the EC is equal to VCC, and therefore EM is equal to VCC. So ZA has to be conjugate with Z out, or the output impedance. Therefore, at the maximum power, where m is equal to 1, the audio amplifier impedance will be equal to the VRMS squared over the audio amplifier power, which results in VA over ICC. Now for the last parameter, which is the output impedance at the carrier, or Z out, this will be calculated at m is equal to 0, because the total power, or the carrier power, should be present at the antenna. So we know that P out is equal to PC, or the carrier power, multiplied by 1 plus m squared over 2. Assuming a 1-to-1 ratio, where P out is equal to PC at M is equal to 0, the output impedance will be equal to the output voltage RMS squared over P out, which then equals the output voltage RMS squared over PC, which results in this equation, which is Z out equal to VCC squared over 2PC. Now, the output produced, or the voltage output produced, will be between 0 and 4 VCC. 4 VCC being the highest power or the maximum voltage achieved. And this is because the maximum output voltage at the output is equal to 2A, where the voltage at node A here is VCC plus EM cosine omega t, as I mentioned earlier, where at M1, EM is equal to VCC. So the largest voltage at A is when cosine is equal to 1, which produces a voltage at A, which is equal to 2 VCC. Therefore, we get a maximum output voltage of 4 VCC. So if we get or if the Z output we get is not equal to the designed antenna, we have to match it using a matching circuit, or the matching circuit that I discussed previously. So we have two types of matching circuits. The first one is the T network, and the second one is the pi network. So the T network sometimes might not be or might not have reasonable values for the capacitors and the inductor. So therefore we use the pi network. And to calculate these parameters, which are L and C, Zn and Z out, and the matching frequency should be used to calculate these parameters. Thank you.